To plan, and then posting these on YouTube. Takes a while. The Regis, the world class is just like incapable of handling much. So I have to have a YouTube channel to get all those things posted up because they're large magnitudes in size. All right, is everybody here for calculus? Calc 1? Outstanding. Hi, everybody. I'm Dr. Trenery, Dr. T. I sent out an email like saying all that stuff, right? Yeah. Yeah, that's generally what I prefer to be called. Let me actually get a piece of paper and find out what you would like to be called and start learning your names. Everybody like where they're sitting? if not, could you like find somewhere you did sitting, just at least till I figure out who everybody is, your faces and all that stuff. So let's see here. Let's make up a little chart. Sorry for not doing this earlier. Let's see. 1, 2, 3, and then this is going to be the front. And I might take a picture of you, and I will not post it on social media or anything creepy like that. It's just so I can learn your faces. So let's see. So there's front. Nobody's sitting in the front row, so we'll just nick it. Okay, so this is the empty front row. And then there is 1, 2, 3 rows. Okay. Well, we can figure this out. So, all right, my friends. So you would be like right here, the two of you, if you wouldn't mind just giving your names. Just tell me what you want to be called, please, and then just include your last name. And I will call you whatever you want to be called. Whatever you like. So it's a seating chart, sit. Okay, cool. So my classes are generally pretty different from most math classes here, for sure. Generally probably different than a lot of just other classes as well. One of the major differences is I like to incorporate mindfulness and a little bit of meditation into my classes. I find that if we come in here and we just clean the slate just for a few minutes, things go a little bit better for you. It's just, and it's also a chance to just shut down for the day for just a few minutes. You spend your whole days walking around trying not to get COVID, listening to people pump information at you, thoughts filling your head, anxieties filling your head about your classes, uncertainties. Now let's just take a few minutes every day that we need to just be. Just here, turn off the thought factory for just a few moments, or at least stop giving it so much credence. And then we'll come back and we'll do math, and the math will end up being spectacular after that. Let's see, did I start recording? I don't know. I think I did. Yeah, great. So, you do not have to participate in this. I'm not trying to indoctrinate you into any sort of cult or anything like that. I don't really care if you want to do this or not. All I ask is that you sit quietly and roughly still while those who want to participate do. So let's do that. Let's do our first one today. And yeah, let's hold on to that just for a minute. So sitting up straight, maybe have your feet on the floor, whatever you want. Just take a few minutes to honor yourself with this practice. And you probably, how about closing our eyes? They're open all day long. So just closing our eyes and settling in. Just noticing what that's like. Noticing the pressure of the seat on your body. eyes closed, what do you make of your body? With no preconceptions, just based on your direct experience right now. What does your body feel like? Notice the sounds in the room. Find yourself drifting into thought, planning, thinking about something that happened earlier today. That's okay. Just gently and kindly bring yourself back to noticing the sensations and the sounds. Now take a moment to make a smile in your mind. You can make one on your face too. What does it feel like to smile in your mind? Think of something you're grateful for. And then let's just gently come back. Do some calculus. Which I hope you're grateful for. It's certainly something to be grateful for, right? What an utter privilege we have to be here learning math. Think of the billions of people in this world who would give anything to just be here for this class period, right? We are truly blessed and privileged to be here. And I certainly feel that way. And I'm glad we're in person. I was scared. I was filled with fear, just about COVID and all that stuff. But now that we're all here together, I think this is a real good thing. We'll see how long it lasts, right? Hopefully everything stays cool, infection-wise, and we can keep doing this. Let's see, a couple of tidbits right up the front. So we will meet in here in person Monday and Wednesday until someone tells us we can't do this. Friday, we will meet Zoom for at least the next 3 weeks. And I will get that information to you very soon. It'll just be a Zoom link and we'll meet, and I hope you all come. A lot of times the Friday sessions end up being problem sessions where we kind of just work together on a bunch of things. Maybe work on the homework that I'm going to give you in just a minute. It'll open in an hour and 5 minutes. But that's the basic plan for today. So let's see here. Let me just go through Johnson. We got the seating chart going around. All right, stuff you need to do. Stuff one. Stuff to do. The first thing is check out the syllabus online. I'm not going to go through that in detail. I'll hit the highlights in here. we'll go through the main parts, and then you can either read the syllabus or continue as probably you have through your career and then barely read the syllabus, right? Like, who reads those? Nobody reads those. They're tonal. But if you read them, that's cool. And man, thank you. I give you great props for doing that. But here's your stuff to do. There's a thing called the CCI Quiz. And this is in world class. So this is something we use for assessment. And we use it to see what people are learning and what they need to learn. This will take you 1 hour tops. And your performance on it is irrelevant to your grade. Simply doing it is the grade. So this is like the greatest grade thing you're gonna have the whole semester, maybe your whole Regis career. You just gotta freaking do this, and you'll get full credit. So this is worth 10% of your grade. I wanna make it worth your while and encourage you to do it. So it's 10% of your grade, your final grade. 5% now, 5% when you take this again at the end of the semester. What I'm going to ask you, and this will make it even easier, it's basically a bunch of calculus concept questions just to see where your understanding is at right now. If you don't know something with 100% certainty, if you like look at this question and it's multiple choice, and you're like, I don't know, don't guess. Please, don't guess on this thing. So I've never even given this instruction before, but we've been looking at the data, and it seems like people are guessing at the start because you feel like you should, right? It's totally cool to leave stuff blank, and in fact, it'll look better at the end for you, for me, if you look like you learned more. And in the beginning, if you guess a bunch of random stuff, you might actually guess it right, and then at the end of the semester, you don't guess, and it looks like you learned less. Don't answer if you don't know. Makes it easy. 1 hour tops. This is due next Friday. So that would be what is next Friday? 10th, 7th, 21st? Anybody know?
Yeah,
The 21st, thank you, beautiful. So this is due end of the day, Jan 21st. Do it sooner than that. I'll end up having, the only thing I hate about this thing is having to nag people to do it. You'll learn this about me, I hate being like a cop. Like, I can't police people. I'm so terrible at authoritarian type activities that I just despise doing it. So please don't make me beg. I will beg. I'm not like an order guy, I'm like a please, please kind of guy. Don't make me grovel. Please just do this. Because if you don't, this would suck to lose 5 points right off the top. So that's the first thing you need to do. Second thing is, oh hell, let's look at the syllabus together. Let's see if we can maybe get it up there and see what it looks like. Does that look like it's on?
I don't think so.
I don't think so either. Yeah, that doesn't look very on. Let's try that. Let's try this. I want to show you where your homework will live. And where all sorts, world class, hopefully you're somewhat familiar with. PC looks select. Oh, this is beautiful. I realized I forgot to put a link to this up in world class. So, sir, if you could put your phone away, that would be awesome. Thank you. And so your homework is mostly going to be here in a system called WebWork. And like I said, I'll put a link up to it, but here's how you can easily find it. If you just go webwork.regis.edu. See, and then it says go, it'll take you there. There you go. So our class is Trinary Spring 22. And what I would like you to do by Wednesday is log in here. Now, how do you log in here? Your username is going to be the prefix of your Regis email address. So if for example, your Regis email address was gopherking777@regis.edu, your login is gopherking777. That's not somebody who's in here right now, but that's your username. So your username is this prefix. Your password should be your Regis password for email. And what I need to know sooner rather than later is that I actually entered all this stuff properly, because I have to do it manually. So if you could please, just by Wednesday, that's assignment 2. You could even make it assignment 1 because it's a little more imperative. Please just try to log in. By tomorrow, I'll have instructions repeating what I just said, put up on World Class for you in case that's not clear anyway. And then just shoot me an email if that doesn't work. You already have an assignment. The assignment will open up, and it's a review assignment. It's kind of pre-calc stuff, but it's to get you working with the system, get you warmed up mathematically, and yeah, but mainly those 2 things right there. Let's take a look at our syllabus, since we are here. So back in World Class, good job, you made it here. Fantastic. In the content, let's look at the syllabus so we never have to look at it again. Unless you're trying to like bust me on something. Didn't you say this contract? Oh, it's the office hours. So right after this class on Mondays and Wednesdays, I will have in-person office hours. When things return to normal, right now I would like to do virtual office hours so we're not in close space together until things chill out virus-wise. If you want to meet, just shoot me an email and we will hook up. We will set up a Zoom meeting. I will have Zoom office hours every Thursday from 2 to 3. Pandemic or no, those office hours will be via Zoom. And then it should stay there Friday, I think right after our class right now. So when we meet, how many people, okay, so let's just think right now. Monday, Wednesday, right after this class, Thursday, 2 to 3, and then Friday after this class. Is there anyone who can't make one of those office hours? Ooh, which you can't make any of those? Do you have a class before this class?
Yes.
We'll figure it out. So you and I, if you want to meet, we can figure out lots of times on Thursday, and we'll just get together. But just communicate with me, okay? That's good. Thank you. So Alex, you've done that, or you haven't. You're in this class. You might have needed that. Oh, look, there's a link to the web work. That's great. Learning outcomes. Well, you're going to learn stuff. Go see what that is there. Here's our schedule. I actually end up, like, out of all the schedules I've ever made, this one I stick to the closest. It's amazing that I actually can keep this on schedule. We will have 3 exams, and they're about a month apart, each one. 3 exams and a final, and they're about a month apart. So you can see the first one's already at the end of January there. And these are not precise. This just don't look at this and go, oh, on Friday of this week, it looks like there's an exam. It's roughly around there. I will give you a week's notice at least on everything that I would ask of you. So you'll get a week's notice. I'll give you review materials, tell you how to prepare for the exam so you can succeed. So then that's way off, but I won't leave you hanging. I won't try to surprise you. I don't do surprise quizzes, anything like that. Okay, so let's see here. Oh, it seems like that schedule looks a little wonky already because we don't meet next Monday. I'm gonna have to fix this. I think I didn't update this. This might not be the most recent version of this schedule. I'll fix it, let you know. Policies, cell phones, no thank you. Let's not do that. That's cool. I think we're all on board with that. Calculators, you don't need no calculator. I don't like calculators. You don't get strong with a calculator. You know, if let's see, what, I don't know, I'm not gonna come up with some dumb metaphor. I want you to become strong mathematically. I want you to have strong math muscles. And so I'm going to show you a bunch of tools that will help you not need a calculator. I will never ask you to do some crazy thing. What is the cosine of 2.1 pi? And expect you to know that. But I will ask you what is the cosine of pi over 4 and expect you to be able to figure that out. I'm going to help you figure that out. So this class isn't going to just make you calculus strong, it's going to make you mathematically strong. And we'll work together. No need to be stressed about this. We will go slowly, methodically, with great warning and love. We will go together. Participation, I just want you here. I want you here playing along and asking questions when you're confused. Let's see, Alex, blah, blah, blah. Well, none of this. Here, let's go down here. Each of the 4 exams is 15%. So that's 60% of your grade from exams. Web work and homework is 30%. So the web work, let's talk about that again. Here is a chance to get 100% easily. The web work is set up so that if you miss a question, you can try until you get it. There's unlimited chances, infinite attempts on the web work. So there's no reason to get anything less than 100% on that portion of your grade. Now, how many people do that? Not many. I don't know why. How many people just don't do the web work sometimes? Lots. Don't be that person. That's silly, right? I mean, you're certainly paying something to be here. Let's optimize those funds. Let's get the most out of our money, most out of our education, and just freaking ace that 30%. You'll have plenty of time to do it. What would be cool is if on Wednesday, somebody's looked at these problems, you started, and you ask questions. And I will answer questions if it takes the whole hour. If we can't get to the material, okay, oh well, we're doing something. We're answering math questions, we're learning. So please ask questions, please be proactive. Own your education. Let's see, okay, the rest of this is just, important stuff, but good Lord, lots. That's it for that stuff. Does anyone have any administrative bureaucratic questions? How this is going to work? No? Okay, cool. Let me, while I'm here, and I've got this up, one of the great resources that you will want to use, especially when you're working at home on web work, or occasionally I'll say bring your laptops in and we'll do work together on web work in here. Like we'll have a problem thing. Come in here, let's get our homework done together, where I'm here to help. If you don't know about this website, desmos.com, this will be an incredibly useful tool. The graphing calculator here is the best. Literally the best. You can come in here and type the greatest, the lovely equations. Look how it even starts knowing that I'm doing that. And then I create something like that. Ooh, I would like that to die a little bit. So hold on, this is a plot function like that. Look at that. Now I can zoom out. Ooh, while we're here, let's look at a freaky one. I love graphing. It's a sine of 1 over x. Look at this function. So see, what's cool about Desmos is, maybe this is similar. When we get better into the realm of mystery and wildness, as we get deeper and deeper into there, we will look at this function somewhere along the line. In the next 3 weeks, we'll come back to this. but truly a great resource. Desmos.com. Keep it in mind, put it in your notes, visit it often, even just for recreation. Come here and just make shit up and put it in there and see what it looks like. Now is the time. When you get out of school and you're busy doing your career, you're not going to have time to go mess with Desmos. I'm begging you to go mess with Desmos now. Now is the time for curiosity and exploration and not shutting off opportunities. All right, that's blah, 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 blah. Let's do some calc stuff. All right. Just making sure we've got everything. I got one more thing for you. Our book. There is a, I don't know if there's a link for it yet up there. I might have to put that up. I might have screwed that up. But our book is free, and it's called Active Calculus. Really good book. Open source. I love free books. You pay enough to come here. You pay so much for books, and there's such a ripoff. It's such a racket, the academic book market, that as much as I can, I go for free books, if they're quality. This is a high quality book. So you're looking for Active Calculus, the calculus book. These got like multiple ones. We're looking for the single variable calculus. Again, I'll put a link up. If you like more variables, you'll have to wait till Calc 3 to do that. But I would like you to read section 1 and 2 for Wednesday, if possible. And I will give you readings. I don't know if you would do them or not, but you'll come out better if you do them, right? It gets your mind just totally prepared. You come in, it's not the first time you heard it. And it will make the things resonate more deeply when we come in here to talk about it together. Okay, cool. Calc time. Nice. So, I'm smiling really big right now. I don't know if you can tell. But man, do I love teaching calculus. This is an honor to be here, to be able to do this with you all, because calculus is one of the greatest accomplishments of humanity. Calculus is, if you don't know what calculus is, you have no idea how profound it is. It's such an integral part of who we are and how we relate to the universe that it has been around since the first civilizations. When we go back to the Fertile Crescent, when we go back to Mesopotamia and Sumeria and Acadia, when we go back to those primal civilizations, they were doing calculus. Back in Babylon, we always like to think that we're so great, how we're so modern. We're doing shit that's been around for thousands of years. Somewhere got lost, and then like people like Isaac Newton and Leibniz pretended like they discovered it. They did good. They made it good. But we're going to talk about Newton a lot, probably Leibniz a few times. They get all the credit for it. But when we go back to these primal civilizations, these folks were doing amazing stuff. For example, in Babylon, they were computing the motion of Jupiter across the sky using integration. Integration is the thing we'll get to the last couple weeks of the class. They were using integral calculus to compute, that's the thing, I'm going to say it again, because every time I say it, it just gives me chills, to compute the motion of Jupiter across the sky. Right, we always think that they were like, oh, that's the great god Marduk up there. No, we must be worshiping Marduk. And they had that shit going on. And we still got that shit going on. But they were scientists. They were brilliant. And they were doing what we're going to do today. They were computing the volume of boats using math that we'll get to eventually. And they certainly were doing the things that we're going to start doing today. Get rid of gopher king. We're good to go. Okay, I am going to, let's start off with an example and have some discussion and thought, because you've just been listening to me so far. So let's let S of t equal the position of a particle at time t. So let me be more precise about what I mean. S of t is a particle on a line. So think of it as like a bead stuck on a string. So here's a line. Here's a bead. And if this is 0 right here, whatever this distance is S of t right now. So S of t equals its, I don't want to say distance, position relative to 0. Spelling and legibility, not my strong points, so let me try harder on the day one. Position relative to 0. So for example, if this was 0 and I was over here and this distance here was say like 3 meters, and this was the position of the bead right now, this would say S, and let's say this is at time t equals 2 seconds. Got 3 meters there. I would denote that like this. A negative says I'm to the left. If I had this, here's the string, here's 0. Let's say at 5 seconds, t equals 5 seconds. And the bead is out here, and this is 7 meters. Then we would say S at 5 seconds equals 7. So right now I'm assuming my units are meters and seconds, but they could be anything. And they're not going to be terribly relevant for what we're going to do. So we're thinking of a bead that's kind of moving back and forth on this string. Now I'm going to make some graphs. So consider the following position graphs. The first one is going to look like this. Here's time, that's my time axis. This is my position axis. So this is S of t. You can just call it S if you want. And let's say that this is 2, and this is in meters. Let's stick with that. And this is in seconds. And what I'm doing is I'm keeping track of the position as time changes. And it looks like this. So that's the first one. The second one looks like this. So this is going to be, let's say that's 4. It kind of looks twice like that one. That's 4 meters. And we start off there. And then the position goes this. And let's say that this right here is, oh hell, let's go 5 seconds. Right at that moment. And then I got one more. Time, position. And we do something like this. This is going to be a little weirder. Time won't be terribly important here. So what I'd like you to do is take a minute. I'm going to use this moment as a quick restroom break. What is the movie associated with each one of these? Okay, so this bead is doing something in each one of these scenarios. If I held the string up in front of you and made a little movie of it, what would the bead be doing on the string? What would the movie look like? as time progressed forward. So I'm going to run to the restroom. I'll be right back. Take a few moments to congeal that. Yeah, talk, that's cool, I like it, that's good, yeah, that's exciting. Oh yeah, we do the picture. Oh, we're gonna have to do multiple pictures. Everybody just like smile real quick, whatever, you know, is good. Smile with your eyes. Just real quick, thank you. 1, 2. Many thanks. Great. Like I said, you will not see those somewhere floating around in the internet. I do this is so ass backwards, really, because now I have to like do this to look at you. Alrighty, let's gather and talk. Olena? Is it Olena? Oh, did I say your name? Sorry. Yeah, Olena? Is it Olena?
Olivia.
Oh, Olena. Got it. Oh, that's okay. Olivia. Got it. I was like, man, I put that V and that I together. Let me just. What an interesting name. Olivia, you were having a chat. You and Clara were chatting about this. Which one of these were you thinking about?
We talked about all of them, but I can talk about the first one.
Yeah, I like it. What were you thinking? What's the movie?
It's not moving.
Yeah, why do you say that? That's good.
Well, it stays at 2 meters at times
Solid, beautiful. So, no motion at all here, right? It starts at 2 meters at time 0, never diverges from that 2-meter mark. So this thing right here is, I don't know how we're gonna draw these movies, but if this is 0 and this is 2 meters, the bead is stationary. Awesome, yes, yes ma'am, thank you. Let's see if anybody else wants to talk. We want to come back. I know you've been actively thinking about this. So I do like to call on people. Kendra?
Yes.
Yes, I said, okay, good. Oh my God. What do you think about number 2?
That one is getting closer to 0 and then goes to the negatives.
Nice. Okay, so how do we feel about that? Starts off at 4 meters. So what you have to do is you kind of almost want to make a little time slice, and you can think of this with little vertical lines. Each vertical segment is essentially a picture of the string at an instant. So it starts off at 4 meters. We start off here. So this is t equals 0. If this is 0, we're at 4 meters, and the bead is right here. Notice that in the next slice, as t progresses, so this is t increasing, the next one is slightly less distance. Let's see if we can even estimate. Wow, that almost might even be 3. Might be 3 meters, if I'm being a little liberal and generous with myself. So in the next picture, we're at 3 meters. And then the next picture, we're at 2 meters, and then at 1 meter, and then at 5 seconds. This is cruising this way. At 5 seconds, so when t equals 5, we are, as Kitcher said, right on 0. Oh, whoop, sorry, 0 meters. And then we start, we keep on cruising. The next one, we're actually falling to the left of 0. So you take this picture. If this is difficult for you, you could flip these horizontally. And they're giving you a picture of the string. So flip this thing horizontally. Here's 0. That looks like a -1. So maybe we could even say, at say t equals 6 seconds, we look like this. We're at -1 meter. Yeah? So yeah, okay. So there's lots of, let's think about this. Okay, so imagine a string going across the room. Here's the, let me find something more bead-like, like a cap. That looks like a bead, okay. Little bead. So, and then here's 0, right here. It starts off like right here, so looking at that top picture. Here's 0, here's my displacement. That's definitely not 4 meters, but it's 4 somethings. So the thing is moving like this. We cross 0 at 5 seconds, we keep moving in the negative direction. As far as we can tell forever, we don't really know what happens beyond that. How is it moving? There's lots of ways to move, right? It could do this. It could do this. Could do this. What's it doing? What's the movie, right? Because this is just like scenes from the movie. Yeah, yes, sir.
It's a constant speed.
It's one?
Yeah.
Yes. What was it, sir?
Constant speed.
Yeah, so what's giving you that sense? I love that, that's right.
Well, it's a linear function, so it always stays the same, what do you call that? Slope.
Solid, beautiful one, thank you. So let's check this out. Juan is suggesting that this indicates constant velocity. Let's see why that might be. Check it out here. How much did my position change over 1 second? So from 0 to 1 second, my position went down 1 unit. From 2 to 3, from in this next interval, 1 to 2 seconds, how much did position change? Went over 1, went down 1. So check this out. I'm going to write slope. Does m equals -1 in each one of those? Is m a cool letter to use for slope? Does everybody have that in your consciousness somewhere along the line? Y equals mx plus b. Sorry, it's like way down here on the ground here. Yes. So notice how the slope in each one of these intervals is identical. Here it's down 1, over 1. So that slope seems to indicate a consistent and constant rate of change. Awesome job. Really nice one. What is the rate of change here? What is the slope?
0.
0. Yeah, no slope. 0 slope anyway. M equals 0. So you can think of this slope. Let's make our first correlation here. Slope seems to somehow be involved with velocity. So with that in mind, could someone who hasn't maybe talked yet, tell us first off, what is the picture? So if somebody wants to just do that, leave the rest. What is the movie here? Nina.
It's getting gradually further and further away from 0 as time goes on. But as it gets away from 0, it goes faster away from 0 and then slows down, I guess.
Yeah, that's perfect. Does everybody see this? Check this out. So this thing here, and let's try to get a handle on what Nina was telling us. Let's say these are our time units. Here's 1, 2, 3, 4, 5. Let's go all the way out a little bit here so we can see some things happen. So in this first second, look at the rate of change here. That's a pretty steep slope. If I were to pretend that was a line, that's a very steep slope. So here we have a super fast jump from 0 to this position. In the next interval, it slows down a little bit. How much did we change from here to here? Well, just about that much. So that change there over that. And right now, you can think of the height of these rectangles as proportional to velocity, roughly. And then as we move over, look at how we're starting to change less position over that same amount of time. And then we get out here, and oh my God, it's almost not moving anymore. These are looking really shitty. I'm sorry. So like right here, so M is like 0 there almost, right? It's barely moving. It's got a little bit. And then it just looks like this thing is decelerating. So we see some deceleration in this thing. So the picture is like this. Starts at 0, wicked fast, slowing down. Barely moving at all. And we can actually see, it looks like it's approaching some distance right here, some maximum distance. It's just getting closer and closer to that. Does this make sense? Fantastic. This is calculus. We're doing calculus, kind of. We're thinking calculus-wise. We're thinking like a Babylonian, and there's no higher praise. So let's get a quantity. This has all been very abstract. Let's get something we could apply to this to give quantitative meaning. Keep an eye on the time. Cool. So let's make a definition. So suppose that S of t equals the position of a particle or object. Particle sounds like we're doing something pretty heavy with like a, the Large Hadron Collider or something like that. It's just like some stuff. Could be a ball, could be a hat, could be a kitty, whatever you want. Position of a particle, and that's not spelled very good. Particle at time t. The average velocity of the particle, we'll just say the noun of this or the object of this will be the particle. The average velocity over the time interval A to B is, and this is the notation of our book, we write AV, the time interval, equals. Here's how it's going to work. I'm going to draw a picture to show you. Here's A, here's B, here's time, here's position. If we're here at time B, and we're here at time A, so that's S of A, that's S of B. The average velocity is the slope of this line segment right here. So the slope of that line segment is going to be the position at the end minus the position at the beginning over how long it took. So let's draw a little picture here. If I make a right triangle, this is S of B minus S of A. This is B minus A. And this is just the slope of that line segment right there. And we can write this, let's write this in a slightly different way that's suggestive of things to come. This is equal to, let's get some nice notation, the change in S over the change in time. So that's the change in S over the change in time. So this is a capital Greek letter delta. We might somewhere along the way see the lowercase delta. So that's capital delta. Lowercase delta looks like this, quite beautiful. That's lowercase. And this is used in almost every science as an indicator of change. Is anybody, any physics nuts in here? Anybody know? So, I'm just curious. Don't write this down. It just came to my mind. And this is going to happen all the time. Forget whose equation. Does anybody notice if S is entropy and entropy is the disorder in the universe? Have you ever seen this? So this basically is the equation that tells us that time just moves forward. It says the change in entropy is always non-negative. Time never flows backwards. Things always tend to become more disordered and dissolve. And that's why everything's so precious, right? This is the equation in physics that makes life so beautiful. So transient, never the same, always fleeting. And that's why we should be grateful to be in a freaking calculus class right now, despite how tired you might be of calculus at this point, because it hadn't even started. I hope you're not tired. Let's find some average velocities. Now math is good. Now we're doing some math. This is going to be a review. I like to sneak the review in. to our lectures, our time together. So instead of a picture, I'm going to give you some functions. All right, so I'm going to help you with the first one. Let's find some average velocities. And exclamation point, because that's fun. Soothing. I don't ever get stressed about stuff in here. Just soothing. Soothing math. Nobody knows what you're doing. And if you get it wrong, who gives a shit? It's just some stuff on paper. It's just vapor. It's okay. We'll figure it out. So never be afraid to try, for sure. So let's do case one here. Let's say my position is given by, no doubt, your old friend, the sine function. How many people feel pretty confident with trig? Yeah, okay. I'm seeing one pretty strong nod. I'm seeing some, at least everybody's still making eye contact, and that's pretty good. All right. So this is, what is this particle doing? If this is the particle's position, we need to sketch this out, just like we did with these before. Let's sketch out the position function. So here's S of t, and here's t. And this is one of those things I'm going to want you to be able to do without a calculator or Desmos or somebody who knows the sine function, because you're going to know. If you know this picture and another picture, you know cosine, you really own a lot, and this is going to improve your scientific understanding vastly, to just be able to make this picture on your own. So let me show you how to sketch a sine. First off, what is sine? What the hell is sine? Let's begin the review. If I take the unit circle, this is 1, minus 1-ish, minus 1. And I think of this as my standard position right here. So this right here is home base, that direction. And I'm going to imagine pivoting that radius around here. So if I pivot that radius a certain number of degrees, we could say. Let's just call that t right there. Imagine just pivoting that a certain number of degrees, or however, the radians is what I want to think, but right now I don't want to freak you out if that's not real common. And I draw a right triangle here. The sine of t is this length right here. It's that height. So it's the height of that triangle that I'm drawing inside there. And this distance right here is the cosine of t. Now thinking of this picture, I can now make a sine graph, rough, more or less. Let's get one other thing set up. How many degrees is a full revolution?
360.
360, beautiful, right? 360 is a full revolution. We will rarely do degrees in here. We will use another measure of angle called radians. Let me explain to you what a radian is. If this is the unit circle, what's the circumference? What's the distance traveled around the full thing?
2 pi.
Beautiful. Oh yeah, it's 2 pi. Because you got a circle of radius r, its circumference is equal to 2 pi times the radius. That's how the distance around the circle. So if I've got a unit circle, it's 2 pi all the way around. So if you make a full revolution, if you live on this unit circle and you walk around, you'll have traveled 2 pi units. if this is meters for that one, it's 2 pi meters, like 6-ish meters all the way around. So radians are the distance traveled on the unit circle. So right here, this would be t equals 0 radians, because I haven't moved yet. When I'm pointing that way, no motion. If I do a full revolution around, I've traveled 2 pi radians. Let's actually draw some other pictures. So I want to refresh your memory on this, if it needs refreshing, and if this sounds pretty alien, I want this to make sense to you. So if I've got a unit circle, and I travel the full distance around, from start to end, and that's 1 unit right there, then that's 2 pi. This is the distance. What if I just travel half the distance? How far have I traveled? Pi, yeah? How many degrees does that correspond to? 180, so check this out. 180 degrees means you've traveled half the unit circle, pi radians. So this right here, so this is 180, this is 360. This is pi radians. That is 180 degrees. And at this point, we can just kind of work from here. What is 90 degrees in radians? Look at this.
Pi over 2.
Pi over 2, divide that 2. How do you get 90? You divide by 2. So check this out. From here to here, I divided by 2. From here to here, if I divide by 2, pi over 2 radians equals 90 degrees. Cool, cool. Is this making sense? I want to see everything's eyes. All right, cool. This is good. So, what's 45 degrees?
Pi over 4.
Pi over 4, because it's half this, right? What's 30 degrees?
Pi over 6.
Yeah, to get to 30 degrees, you divide by 3. Divide by 3. So pi over 6 is 30 degrees. What's 60 degrees?
2 pi over 6.
It's twice this. Yeah, that's it. Yeah, it's twice. 60 degrees twice each side, so 2 pi over 6. Or just pi over 3. Beautiful, 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 beautiful. So that's the basics of radians. We're going to come back to all this many, many times. So let's think as I do a full revolution. So this is going to be in radians. And I know that I start at 0, and as I spin around, that's 2 pi. So what is happening to sine? Let's draw this picture here. When I have 0 degrees, I've got a dead triangle. There's no triangle here. So the triangle kind of looks like this. Let's fake it out. It has height 0. And this leg and the radius are 1. The sine is this side, so it's 0 right here. So sine of 0 is 0. What happens as I move up? What is happening to the sine? This opposite side length, look, goes from 0, increasing, increasing, and it maxes out right here, and then starts to decrease as I go out here. What is the maximum?
1.
1. And that is at pi over 2, aka 90 degrees. So at pi over 2, let's see here. There's 2 pi, there's half of that, there's half of that. What's that one then? What do I label?
3 pi over 2.
3 pi over 2, beautiful. It's 3 of these halves. 1 half, 2 halves, 3 halves, 4 halves. So at pi over 2, I'm at 1. What's the height of this triangle right here that's just right there and flat?
0.
0. tricky time. Now what's happening? What's happening to that height? Is it positive or negative?
Negative.
It's negative. It's becoming more and more negative. What is its least value? What is the
-1.
-1? And that's at 3 pi over 2. And then, as I move up this way, it is shrinking back to 0, or increasing back to 0. So I'm back here, and here's the motion. Now, here's not how you sketch a sine curve. That's garbage. That's a sawtooth, or something like that. If you were to play this, let's see. Oh, damn, computer's gone. Let's see, how much time do I got? Hold on, I want to play something for you. So, waveform sounds. Let's see, triangle wave, I think that's what that is. Okay, so if this thing right here, if this represents sound frequency, here's what that sounds like. Okay, we're good. What does a sine sound like? The sine is a beautiful curve. So notice how buzzy that was? Sine looks like this. What does that sound like? So this is it. This is about the last little demo I'm going to do. So sine wave sounds. Here's a sine tone. Here's one for 10 hours. Okay, whatever. I'm getting worried. Can you hear a difference? You hear a softness. There's less buzziness to it. And on Wednesday, we'll pull it back up. But a sine wave is, okay, stop, dude. That's good, thank you. So a sine wave is a smooth thing. It's a beautiful creature. And if you want, then you can repeat this over and over again. Let's get a cosine curve up. We'll come back to this problem. We're going to pick up here on Wednesday, but I just want to finish the trig review part 1A. So this is sine. Other trig stuff. We'll come back to this analysis, and like I said, probably at the start of the hour on Wednesday. Let's look at a cosine curve. So now again, cosine is this distance here. As I move along the circle and look at how this distance is changing, notice what it's at right here. When I have that dead triangle, cosine is that distance, it's 1. As this moves around, look at what happens, it shrinks. It's 0 right there at pi over 2, becomes negative, now it's at -1. Now it's shrinking back to 0, increasing back to 0. And now, again, this distance here, how is that changing? It's becoming longer and longer as I move up this way. So cosine looks like this. Here's how you do a fast one. 2 pi is your period. Mark it off halfway, another half, and then that half. 1, 2, 3, 4 halves. Max amplitude, min amplitude. Draw a little box. Cosine starts at 1, comes down to 0 at pi over 2, hits -1 at pi, comes back up like this. So this is cosine. This is t. This is cosine of t. right here. And then if I want to repeat this, this goes on forever in both directions, cookie cutter. Whew. Okay. Sorry, I'm trying to think. Let's call it a day. That's a lot. That was a lot of a day. And we'll start here on Wednesday. Please give 1, 2 a read if you have time between now and Wednesday. And keep an eye out for announcements. I will see you all. Thanks, everybody. Nice meeting you all.